Hi folks, in this video we're going to talk about equivalences and Venn diagrams for conditionals. So pause your videos and see if you can answer this question. Which of the sentences from this list, A through G, have the same true function as P arrow Q? Which of them are equivalent? Okay, I hope you paused your videos. What you would need to do to answer that question is compute the truth functions for each of these, and then check to see which of them have the same truth function as arrow, which of course is TFTT. So you could have quickly solved each of these with a four-row truth table. If you did that, what you'll discover is that there's actually three of them that all have TFTT. It's also quite obvious why each of these three have the same truth function. Of course, if not P or Q has that same function, this D is just the same formula by commutativity. And F is just a version of De Morgan's off of A. So clearly those three in red have to have the same truth function, and they're all the same as arrow. This is one of the key equivalences that you need to know with the conditional. I call this the Boolean definition of the conditional, or BDC. So anytime that you have an arrow, you can actually turn that into a disjunction as long as you put a negation on the antecedent. This is really important knowledge. And because of De Morgan's law, that's also equivalent to just a sentence that is a conjunction with a couple negations on it. Now, one thing that tells us is that adding the conditional to our language does not give us more expressive power. Anything that we could have formulated with an arrow, Boole could have done too, just with disjunction and negation. So you might be wondering, why even add arrows to our language? Well, it's not natural. It's not very useful to transform if-then claims in English into ors. Disjunctive reasoning, like proof by cases, does not easily capture the way in which we reason with conditionals. So it's going to be really helpful to have these because it makes for a better model of natural language reasoning, like how we reason in our everyday lives in English. But it doesn't mean, from a logical point of view, there's something special about prop. So the important thing to realize is we're adding it because it's going to make it a more useful model, but not because this logical system is then going to do wildly different things than Boole could have done. Another key equivalence that you need to know for the conditionals is the contrapositive. That one we talked about already. You can reverse Q and P as long as you negate both of them. That's the contrapositive rule. I think biconditionals, there's a few helpful ways of thinking about biconditionals. One is just to think of it as two conditionals. So this arrow definition of the biconditional is what's really intuitive for me. Of course, there's two nice ways to translate it into Boole. The bottom one here, this is just starting with the arrow definition and then turning those arrows into disjunctions following the Boolean definition of the conditional. Interestingly, there's a wide scope disjunction that captures the exact same idea, and this is a nice clean way of thinking about it. What does A if and only if B mean? Well, it means A and B are true, or not A and not B are true. This captures those two rows of the truth table nicely and is indeed the same truth function as the biconditional. Okay, let's do something more with the truth functions for arrows. Let's see if you can represent them visually. So pause your videos now and give me two diagrams. One diagram for formula number one and another Venn diagram for formula number two. Okay, you should have been able to do this task, so I really want you to pause your videos and practice it. How do you do so? Firstly, you just have to remember that we convert the truth table into the regions of the Venn diagram, just like we did before. There's 8 rows of this truth table, and then there's 8 regions of the Venn diagram. The next thing you need to do is carefully compute the truth functions for these. So you compute the innermost truth function first. Like all truth functions, you have to work from the inside out. Then we compute the main connective. And let's see, where did I get F values for these things? The only way to get an F with a conditional is if the antecedent is true and the consequent is false. So that's why I got one on row 2. Notice that the arrow claim is true on all of these rows down here in number 1 because the antecedent is false, and the false antecedent just trivially makes for a true conditional. So there's only one place on region 1 that's not going to get shaded. The other sentence is different. I actually got 3 Fs on this one. So when I do the Venn diagrams for these things, my Venn diagrams look like that. So one thing this will tell, there's one more bit of information you can glean from this. These two sentences are not equivalent, because if they were equivalent, they would have the exact same truth functions. So what are the counterexamples? What proves that these are not equivalent? Well, namely regions 6 and 8 proves that they're not equivalent. And given that they're not equivalent, they don't have the same Venn diagram. And that tells us one more thing, which is what law would this have been if this equivalence would have held? This would have been associativity. Notice the order of these is the same, but we're grouping them in a different way. So this tells us something. Associativity fails for the conditionals. You have to be careful. Not all the laws that hold for the Boolean connectives hold for the arrows. That's something to be on guard about. So in this video, what we've talked about is the key equivalences that do hold for the conditionals and how to do Venn diagrams for the conditionals. And be on guard, because not everything that held in bool is going to still hold for the arrows. Of course, associativity, commutativity, those still hold for bool, but they don't necessarily hold when the arrow is the main connective. Okay, thanks.